All right, so I want to go through just a few examples here of the alternating series test. So look at some series that may or may not converge using the alternating series test and talk about why they do or don't. So the first example here, first of all, we've got this indicator that we're looking for here, that -1 to the n tells me it's an alternating series. Now, more specifically, it's an alternating series because of that -1 to n, and what's in the denominator here is always going to be positive. So that -1 to the n is going to alternate between positive and negative. So first condition, we can check off it is an alternating series. Second condition, we want to show that the terms are decreasing. So what we want to do is we want to show that 1 over 1 plus the square root of n, which is just the nth term, or at least the absolute value of the nth term, and we want to compare that to 1 over 1 plus the square root of n plus 1. So that's the n plus first term, or the absolute value of it. And if it's a decreasing function, then this one should be smaller than this one. So what we want to look for in this one is that the denominator here is bigger. And when we divide by a bigger number, we're going to get a smaller number. So that means that as n is getting bigger, the terms are getting smaller. So our second condition is also true. The third condition that we need for the alternating series test is that the limit of the terms as n gets really big, okay, and again, we're just looking at the absolute value of the terms, this needs to go to 0. And that's the case. This is a pretty straightforward one. Since the denominator approaches infinity, we divide by a really, really big number, we get a really, really small number, so the terms do approach 0. So that third condition is true. So then we can write out, and I'm going to pretend like I'm taking the AP test here, so I can say the alternating series converges by the alternating series test because, now we need to mention these three conditions here that were met. First one I actually already did. I said it was an alternating series, so first condition is good. The other two, I'm going to say the terms decrease in magnitude. I'm saying magnitude. We could say absolute value here because we're just looking at the absolute value of the terms to 0. Okay, so we've got the decreasing part there, and we've got the limit is 0 there. All right, so we check our three conditions. Those three conditions were met, so we know it converges by the alternating series test. The next example, I'm going to go through those same things. So this part of the expression is always going to be positive because n is starting at 1 and going to infinity. I probably should mention that. And this part is going to make it alternate. So it is an alternating series. That meets the first condition. Second condition, we want to show that the nth term, absolute value of the nth term, so I'm leaving off the -1 to the n plus 1, we want to show that's greater than the n plus first term. So 1 plus n plus 1 over n plus 1 quantity squared. Now, notice on this one that the numerator and the denominator are both bigger. So this one's not as straightforward as the last one. I'm not going to get into the details here, but essentially because of the square and the denominator is more bigger than the numerator. Then we know that it's going to be a bigger denominator making a smaller term. The easier way to handle this is to actually cross multiply. So if we multiply both sides of this expression by n squared, that's going to cancel out the n squared. Get that over there. What I want to keep in mind is that n is a positive number. So in an inequality, if I multiply by a positive number, it's not going to change the direction of the inequality. So if it was less than, it's going to stay less than. And then same thing, I'm going to multiply by n plus 1 squared. And same thing, that's positive, so it's not going to change the direction of the inequality. So we have n plus 1 cubed compared to n plus 2 times n squared. Now these are both cubic polynomials here of n, but if we remember binomial expansions here, this is going to be n to the third power, then it's going to be plus 3n squared plus 3n plus 1. Okay, so that's all the left side. And then the right side is going to be n cubed plus 2n squared. So this makes it pretty obvious, I think, when n is a positive number, the n cubes cancel each other out, and then the 3n squared is bigger than the 2n squared, and then obviously we have this extra 3n plus 1, which isn't over here. So long story short, it is a decreasing function. We could also do this by taking the derivative of this with respect to n and show that that derivative is going to be a negative value. And that negative value then means that it's a decreasing function. So we could also use a derivative there, which in this case might have been a little bit quicker. Last thing here, let's change colors. We want to show that the limit of the terms as n approaches infinity is going to 0. Another pretty straightforward one here. The denominator here is a bigger power, so as n gets bigger, that's going to dominate. And so we'll just say the limit is 0. So all three conditions are met. I'm not going to write out the whole sentence again, but we can say the alternating series converges by the alternating series test because the terms decrease in absolute value or magnitude to 0. Next example here. First part, first condition, it is an alternating series. So n factorial is always positive, 2 to the n is always positive, and this part right here that I have circled is going to alternate, so it does alternate. The next part, it has to be a decreasing function. We can't use a derivative here because we don't know how to take the derivative of a factorial. So I want to compare n factorial over 2 to the n to n plus 1 factorial over 2 to the n plus 1. I'm going to do kind of the same thing I did on the last one. I'm going to multiply both sides by 2 to the n, and that's just going to leave a 2 in the denominator there. And I'm also going to divide both sides by n factorial, which is going to leave n plus 1 over there. Because remember, n plus 1 factorial is n plus 1 times n minus 1 times n minus 2. So everything from n on down cancels. And what we get then is 1 on the left side compared to an increasing quantity here over 2. So as soon as n is bigger than 1, then we're going to get a value here that's bigger than 1, and so this is going to be less than. This is an increasing function, so each term is bigger than the term before it as soon as n gets past 1. So that means that the second condition is not met, and the alternating series test is actually inconclusive. Now, we've got the nth term test for divergence, and if we had looked at this limit from the very beginning, we could have saved ourselves some time here. Remember, factorials are the fastest growing of the 4 types of functions we've talked about. So that numerator is going to dominate, and this limit is going to be infinite. And remember, if the terms don't approach 0, if this limit is anything other than 0, the nth term test says that it diverges. So if we're strictly trying to use the alternating series test, it's inconclusive. But the nth term test for divergence says this is a divergent series. All right, one more here. This series is a pretty unique one, I guess. It's got 2 things here that could make this an alternating series. So that -1 to the n plus 1, this does alternate. What's going to happen here, though, with the sign is that the sign of n is going to be sometimes positive, sometimes negative, but does not alternate. So if this had been sine of, say, pi n, well, that's just 0 Okay, so that's kind of trivial. But let's say it's sine of pi over 2 plus n pi. That is also an alternating series. And so an alternating sine times an alternating sine is going to make it a not alternating series. But in this particular case, we don't have those pi's in here. So this right here, sometimes positive, sometimes negative, is being multiplied by a series of these ones and negative ones that is alternating. So this is not an alternating series. This series does converge, but it doesn't converge because of the alternating series test. So the alternating series test is inconclusive here because it's not even an alternating series. So don't try to use the alternating series test on a series that's not an alternating series.